So let's review what we've covered in Unit 7. Unit 7 is about Lorentz contraction. And Lorentz contraction concerns how lengths change in different reference frames. So we started by asking the question, what is length anyway? And settled on this definition. The length of an object in an inertial reference frame is the distance between simultaneous measurement events occurring at each of the object's ends. So if I want to know how long something is, I want to do a space-time measurement here, and those measurements need to be done at the same time. So simultaneity here is the key. So then, a couple of different ways, we derive the formula for Lorentz contraction. Here it is. R is the rest length, the length of the object in a reference frame in which that object is at rest. You could think of it as the true length. If you're in a reference frame that's moving at a speed beta, then this will be the length of the object, and it will be smaller, because this number is always smaller than 1. Similarly, if we're at rest and the object moves at a speed beta with respect to us, we'll also observe the length to be contracted to this amount. So there's a symmetry here. And again, we derive this a couple different ways, and the key step in the derivations is to realize that simultaneous measurement events in one frame are not simultaneous in another. Simultaneity is relative. It's a frame-dependent statement. All right, so length contraction is weird. Like, in some ways it feels weirder to me than the fact that you can have different times, proper time, space-time interval, and so on. So how do we think about it? Well, here are a couple ways. One, just a reminder that it's not the case that like a moving object gets squashed together because of the forces acting on it. So that's not what this is about. Some ways to think about it are that space and time are intertwined, that there's no such thing as a purely spatial measurement or a purely temporal measurement, because even something that appears purely spatial in my reference frame might not to you, because my simultaneous measurements would not be simultaneous for you. So space and time get all are intertwined or closely related, mixed together. Another way to think about it is that what we call length is just a shadow or a projection of a physical object onto a particular part of a reference frame, the x-axis. And in different reference frames, sort of like tilting a blackboard on which there's a shadow, we'll see different lengths for the same object. There's that physical reality, but it just that's true in there, but it projects down onto a flat surface in different ways. And lastly, we examined one of the famous paradoxes from special relativity, usually known as the barn and pole paradox. So there's a pole that has a rest length of 10 nanoseconds, and if it moves at this speed, it will contract to 8 nanoseconds. So if in the at rest frame, we're in a barn, and somebody with the pole runs through the barn, we would see an 8 nanosecond pole fitting in an 8 nanosecond barn, all at the same instant. In the moving frame, though, the pole has its rest length of 10, and it sees the barn as Lorentz contracted to 6.4, and so in the moving frame, at no point does the pole fit in the barn. There's no way it could. And the resolution to this paradox and other paradoxes like it is again to recognize that what's simultaneous in one frame is not simultaneous in another. So this relativity of simultaneity has an influence on length. So this brings us to the end of Unit 7. In the next unit, we'll step back a little bit and look at some of the broader implications of special relativity. One of the things we'll do is look at the causal structure of space-time. We've seen that the notion of simultaneity is relative, that in one reference frame, events A and B might be simultaneous, but in another reference frame, B might come before A, or maybe even vice versa. So this starts to pose a puzzle. What if event A caused event B? is there a reference frame in which we could say B caused event A, in which time would flow backwards or causality would flow backwards? So we'll look at that dilemma in the next unit. We'll also look at how velocities transform in special relativity, and we'll see that there's no object that can go faster than the speed of light. So all that's coming up in the next unit, Unit 8. See you there.